There we go. Alright, so I am monitoring my own stream and it should be up now. So it takes about, I would say, around 8 to 10 seconds in order for that to pop up. Alright. Sure, we can go over the relation assignment if that is what people want to do. Let's go there then. Alright, so look for relation. There we go, and here's the homework. And I'm gonna take the test, as if I'm taking the test myself. So this way I see the same kind of questions that you guys see. All right, consider the not equal to relation over all integers. Which of the following relation properties apply? Okay, so this time we're talking about not equal to. Partially ordering, we'll deal with that later, okay? Because partially ordering, requires something to be reflexive, transitive, and also anti-symmetric. So we'll check out the other ones first. Is it symmetric? If A does not equal to B, then B doesn't. If and only if B does not equal to A. Yeah, I think we can check that. Reflexive? No, we cannot check reflexive because if we're looking at one single integer, it does not equal to itself is false. Okay, so it is not reflexive. Totally ordered means it has to be partially ordered first, so we are not going to answer this question until we can answer the first one. Is it transitive? The answer is it is not transitive, because if you choose 1 and then 2 and then 1 again, so 1 does not equal to 2 and 2 does not equal to 1, but 1 does not equal to 1 is false. So it is not transitive. Is it antisymmetric? So antisymmetric means if A are B and B are A, then A, B must be the same. So in this case, it's quite obvious it is not antisymmetric because 1 does not equal to 2 and 2 does not equal to 1. So, not equal to applies to those two elements. But 1 and 2 are definitely not the same, right? So it is definitely not antisymmetric. So without antisymmetry and transitive, it is not partially ordered, and if it is not partially ordered, it cannot be totally ordered. So symmetric is the only one that we can check in this case. Question number 2. Consider the equal to relation over all integers. Which of the following relations properties apply? Okay, first of all, is it antisymmetric? The answer is yes, it is antisymmetric because if you have A R B, then B R A has to be true too, because A equals to, because in that case A and B must be the same. So it is antisymmetric. Is it transitive? And the answer is yes, it is actually transitive. So if you can find me 3 values, E, F, and G, such that E equals to F and F equals to G, then E equals to G. Yeah, that kind of makes sense, right? I mean, just intuitively, it makes sense already. Is it reflexive? Yes, it is reflexive. A value always equals to itself, so it is reflexive. Is it totally ordered? We don't know yet. Okay, so we're gonna have to look at whether it's partially ordered or not. And then there's one extra requirement in order for that to be totally ordered. Is it symmetric? Yes, it is symmetric. In other words, if A equals B, A equals B if and only if B equals A. Okay, that kind of makes sense. And is it partially ordered? The answer is yes, it is partially ordered, but it is not totally ordered. Because in order for a relation to be totally ordered, then you should be able to pick any 2 elements from the set, and those 2 should relate to each other in one way or the other. In other words, if you choose A and B, then either A equals to B or B equals to A for any AB that you can choose from the set. And it is obviously not true in this case. Okay, how anti and sim. Okay, so that's I'm going to say it's a very abbreviated way to ask the question, and I am going to interpret it as how can the relation be antisymmetric and symmetric at the same time? Yes. So next time you try to be more specific. Like, don't try to save a few keystrokes. All right. Well, how can they be true at the same time? That is it's a very intuitive question, but the answer to that question has to do with how those two properties are defined. So I'm going to ask Mohammed to quote the definitions of antisymmetric and symmetry in the text channel. Or you guys can help too. Anyone can post those two definitions because I want to know that you guys know where to find it. That is true. Antisymmetric is not symmetric. Okay, so they are not the same thing. That's why we have to go back to the definition because the definition is pretty clear to indicate what they are. All right, so Sebastian's got the right approach because the word anti seems to suggest it is not, but that's not really the case, right? It is not the case here. Antisymmetric is not symmetric. Yep, yep. The key word here is did. Whether it's briefly or not, I did. All right. Well, I'm still not seeing anyone quoting the actual definition using the quantified expression in the text channel, which is, to me, that is problematic because, if people are not getting back to the definition and really just try to think of these terms, from an intuitive way of looking at what those words typically mean in an English sentence, that is not going to work. Thank you, Luke. That is symmetric, and here's anti-symmetric from Philip. Very good. Okay, excellent. So in the text channel, so I want you guys to direct your attention to the text channel. Anti-symmetric. Okay, so there's an error, but you guys get the idea, right? So the definitions are actually not the same, right? One is not the negation of the other one. Symmetry is defined to be for all EF in X, EF in R, if and only if FE is in R. So, basically it's saying, okay, you have two variables, E and F. Both need to be instantiated. They need to map to one element in X. Okay, they can be the same, they can be different. So it doesn't. There's no restriction of which element you have to bind E and F to. But the point is, if E and F is in R, then F and E should be in R as well. If EF is not in R, then FE should not be in R, and vice versa. That is symmetry. Okay, if you see one, you should see the other one. It's kind of like a mirror, right? So if you think of symmetry as a mirror, that means a normal person is going to see the reflection. However, if you have a vampire, then the reflection is going to be lacking, right? So that's why if you have things like vampires, then symmetry is not going to work. Anti-symmetry, on the other hand, is saying if you find EF in R and you find FE also in R, so if both are in R, then E and F must be the same. That is antisymmetry. So there are really clear differences between those two definitions. All right, so here we got a few text messages in the text channel. I'm just trying to catch up with that. So Chris said symmetry if ARB then BRA. Anti-symmetry is if ARB and BRA then A equals to B. That is correct. So that is the English way of spelling out the same expressions. And then Nathan said, so equals to is not totally ordered because it is not comparable. Yes, that is true. Because in order for a relation to be comparable, every two element, any way you choose two elements in the set X, those two elements need to be related. Now, which way is it going to be related? We don't care, okay, because it's just an or. But they have to be related in one way or the other, okay? It's not exclusive or, it can be both. It's just that we have to have at least one relation relating any two values from the set. So that is correct. And then Danny said for symmetry, it is if and only if and not just an implication. Yes, that is part of the difference, but the main difference has to do with antisymmetry says, the right hand side of the implication is that those two elements must be the same. So if you find ARB and BRA, then A and B must be the same. And then Marco said, are we not covering asymmetry? I don't think there's asymmetry, so I might be wrong. I can go back to my notes and try to look for that word, but I do not believe that we have asymmetry. Chandra said, I saw references online to asymmetry relations as the opposite of symmetric, but those weren't covered in this module. That is correct. So from what you guys described, I would say asymmetry is the negation of symmetry, but anti-symmetric is not symmetric. You have to go by the definition. I mean, really just kind of go by the definitions. And then Danny said symmetric means ARB if and only if BRA. That is correct. That's without the quantification, but that's okay because without any quantification, it is implied that it is universally quantified. But sometimes that can be confusing as well. In other words, sometimes it is if it's not clear whether it's universally quantified or existentially quantified, it can make a big difference. And it cannot be implied by the context. But in this case, it is somewhat clear from the context that what Danny typed, is universally quantified. All right, so Nathan is still typing, so I'm gonna wait until everything is settled before we move on to question number 3. There we go. I see asymmetric defined as A is less than B implies the negation of B is less than A. Since I have not talked about asymmetric in this class, I'm not really sure how it is defined. So let's just not talk about asymmetric because it is not in the module. And until I find the actual mathematical notation defining what is asymmetric, I do not feel that I qualify to talk about it. Because the way we describe it here can be that's kind of interpretive because I know it makes sense. I know it's intuitive to interpret it this way, but I'm not sure. Okay, so until I can actually see the mathematical definition, I cannot say one way or another with confidence. Alright, okay, so we are just refining certain things to make it more clear. And then we still got a few more text messages coming along, so I'm gonna wait for those two. I mean, this is the kind of stuff that you don't get from an asynchronous class, right? Not anti-synchronous, right? I hate to play with that, but I want to play with that. Alright, so I see it's Yep, this is a synchronous class, and this is why I think synchronous classes help because just look at all the text messages through the text channel. All right. Yep. So antisymmetric has no equivalence in English definition, so the only way to define it is to look at the notes. And I'm fairly sure that my interpretation of antisymmetric, the way I define it, is actually universally true in any type of references that talks about relations. All right, so Ivan is going to finish his typing too, so Wikipedia is one source. There are many other sources as well. I mean, there are tons of textbooks, on discrete structure or discrete math. All right, so Ivan says for antisymmetric, because of the implication, there can be EF, but as long as there's no FE, it would still be antisymmetric. Yes. So if you cannot make the conjunction true because you only got one or none, then the implication is going to be true, because we know with any type of with an implication, if the left hand side is false to begin with, then we go like, the whole thing is going to be true. The implication itself is going to be true. So that's why, that is why in the first week, in the first class, I talked about implication, because implication is super duper important in this class. Exactly. You need a counter example to prove it to be false. It being the implication. I just want to be super clear, what it is referring to. Okay, so the differences between partially and totally ordered is whether it's comparable or not. So to answer Manpreet's question, let me pose another question to you, which is, let's quote what comparable means in the context of relations. Because that is the extra requirement in order for something that is already partially ordered to also be totally ordered. Comparable is the one thing that differentiates something that is just partially ordered versus something that is also totally ordered. So what is the definition of being comparable? All right, so we are still answering the implication question here. So what is comparable? So I'm hoping my response, by not answering the questions directly, makes sense to you guys, because because that really is the important part, right? Knowing where to find the definition and understanding the definition itself is important. Comparable is a property of relation. It is discussed in the module that talks about relations toward the end, because that's the differentiating property between something that is just partially ordered versus something that is also totally ordered. Chris is right. Okay, for all EF in X, there's no either. It's actually just a regular or. But when you combine that with anti-symmetry, then exclusive OR can also be used. But the definition of comparable does not use exclusive OR. It is just a regular OR. So there you go. So Chris, answers the question, even though it's a little bit different from the actual definition in the text. So in the text, I'm just going to type it here. So for all for all. There we go. Okay, Nathan beat me to it. Yep, that's how comparable as a property is defined. So, are there any questions about that definition of what comparable means? So a few things pop up in my mind right now. It just kind of bubbles up in my mind. The first one is I think it is crucial to really read the modules and not just rely on, okay, I attended all the lectures, I got everything, during the lecture, I think I'm good. No, that usually does not work very well in this class. Now, does it work? Is it true that this won't work for anyone? I cannot say that, but I can say that it doesn't work for most people, as in 90+% of people. So that means, after the lecture or before the lecture also, if that is, if you can spare the time, it is important to read the material and not just skim through it. I mean, I really mean reading through it, and take notes and annotate my stuff, okay, with your notes. It's really important to do that because there are a lot of tiny little details, just as what we are talking about here, okay? What is comparable? Okay, yeah. So I'm just trying to help point out, useful study skills not only for this class, because if it's only going to if blah blah blah, if it is only going to be useful for this class, you can forget about it, right? It's not going to be helpful in all of your other classes, especially after you transfer to a 4-year university. So there you go. I don't want to nag, but I want to point out why it is important to do certain things. Trichotomy is also the other name of comparable. That is true. All right. So which one are we talking about? Is the R in this case just referring to the general relation that is totally ordered? So are we still talking about question number 2, equal to? Equal to is not totally ordered because what Nathan quoted is false. I mean, all you have to say is to pick E to be 1 and then pick 5 to be F, right? So 1 equals to 5, no, not true. What about 5 equals to 1? Not true. So the OR is going to be false. So if you have a for all or a universally quantified expression, if you find one case where the expression is false, then the whole quantified expression is false. So that's why it does not work for equality. There you go. It still needs to be reflexive, transitive, and antisymmetric. And yes, so on top of these 3, reflexive, transitive, and antisymmetric, those 3 are required to be partially ordered. Everything that is totally ordered is also partially ordered, but in order for something to be totally ordered, we also need that one extra requirement, which is it has to be comparable as well. So there we go. All right. Yeah, ERF is just a shorthand of in parentheses EF in R. It's just a really shorthand to say the same thing. All right. Something can be symmetric and partially ordered. Yes. Okay, I'm going to give you guys this example, because we actually talked about it a little bit, but I'm pretty sure most people might have forgotten about it already. So I am going to talk about this one here. All right, so I am going to give you a set X that is kind of usual. We got 3 elements, 1, 2, and 3 in it. Okay, so X is no big deal, pretty standard kind of thing. And I'm going to give you R now. R is empty. So now we want to say, what about this R here? Okay, what kind of properties does it have? We actually talked about this. Okay, because we look at the empty relation. It's like, wow, that's kind of weird, right? Does it actually have properties? Well, let's go through all the properties. It is not reflexive for sure because there's nothing relates to anything here, right? So we can say this is definitely not reflexive. And I think I spelled it right. Yep, there you go. So the next one is it symmetric? Well, as it turns out, it is symmetric. Symmetric. All right, it is symmetric because symmetry simply means if ERF if and only if FRE. And then in this particular relation, it's like, but heck, there's nothing, okay? None of these elements relate to any other element. Well, then it's fine, right? Because if and only if means if both sides are false, then if and only if is true. All right, not a problem. And for people who are now thinking, what is that? What are you talking about? I would say rewind all the studying, all the notes and whatnot to week 1. When we talk about if and only if, or equivalency, the one that has 2 arrows, okay, pointing both on both sides, look that up because that is why. Okay. Okay. All right. So I'm getting back to the text channel and just kind of catch up over there a little bit. I feel that the misunderstanding today mostly comes from anti-symmetric. Sounds like not symmetric. Well, yes, okay, I can understand how that can be a reason, okay, but in a class like this, we don't go by what that word typically means, right? We look up the definition, and there is definitely a definition for anti-symmetric, symmetry or anti-symmetric. So I mean, this homework, you guys got a week to do this, right? What is the 5 minutes to look it up, look up the definition? I'm not going to answer that question. It's a question that only people in this class can answer. All right, so getting back to the empty set here, the next thing is it transitive? The answer is yes, it is transitive. And the next question is it antisymmetric? The answer is yes, it is also antisymmetric. Antisymmetric. So the rest, I think you probably get the idea. It is not comparable, okay, and therefore this is not partially ordered, and it is definitely not totally ordered. Okay, so just looking at the empty relation itself, hopefully will help remind people what implication means and what if and only if or equivalency means, because those are very, very crucial definitions that we need not only in this class, okay, but every time we are trying to do anything with formal mathematics. Those words and those operators are really important. All right. All right, cool. All right, we shall move on. It is a common problem that people hear I don't believe X and interpret to mean I believe not X. Not asserting something is not the same as asserting its negation. Yep. Well, okay. They're complete and long philosophical discussions surrounding this kind of um, sentences. And I'm not going to get into those discussions, okay, because that can get me into trouble. Even though it is in the context of logic, it's still not a good idea to get into those discussions. maybe later, but not now. All right, so getting back to the quiz, we're now done with question number 2. We move on to question number 3. If R and S are both relations defined over X, which means they're both subsets of X Cartesian product with X, and we also know that R intersecting with S is reflexive, then what do we know for sure about R? Alright, so the first thing we know about R is it is reflexive. And that's about it. There's nothing else. There's nothing else you can know about R in this case, but you do know it is reflexive. So this is going back to the definition of, guess what? Intersection, right? Because if something is if the intersection itself is reflexive, that means every element relates to itself in R and also in S, because these are the common elements. But we cannot tell anything about whether it's symmetric or not, because R can have one extra element that makes it not symmetric. R can also have two extra elements to make it not anti-symmetric. And also R can have some extra elements, like we need two extra elements in order for R to be not transitive. So not even knowing what is in X, we cannot tell whether the other ones are right or not, but we can tell for sure that R has to be reflexive. Alright, so I'm getting back to the text channel. Because it's not multiple selection, the answer is done. That is right. But sometimes with just one single choice, they can still look really confusing. It's like, but maybe it's this one, maybe it's this one, maybe it's this one, and so on. I did not really try to make it very confusing, so this one should be pretty clear cut. All right, and then Nathan says we know that R is reflexive because the intersection of R and S is reflexive. So R includes all the elements that are in the intersection, and therefore it has to be reflexive as well. Yes, so Nathan's explanation is also correct. All right, so we got 2 more people typing, and I'm going to scroll down unless we have to go back up. For question number 3, For question number 3, that would mean the relation S must also be reflexive. Yes, that is correct. So Ansel made a very good point that not only R, but the relation S is also reflexive. Yes, that is good. All right. moving on to question number 4. Alright, so here's question number 4. Consider the less than relation over all integers. Which of the following relation properties apply? It is not, let's see. Oh, it is antisymmetric. It is antisymmetric because you will never find, A R B and B R A. Something cannot be less than something else, and then the other way around also at the same time. Now you can find two things that are not less than either way, like 1 and 1, right? So 1 is less than 1 is not true, 1 is less than 1 is not true, but you cannot find two values where it is less than in one way, it's also less than in the opposite way. So as long as the conjunction is false, well, the implication is going to be true. So that's why this one is anti-symmetric. It is also transitive. Now this one is kind of intuitive, right? Because if A is less than B and B is less than C, A is less than C. So that is just kind of intuitive. It is not symmetric because if A is less than B, there's no way B is going to be less than A. And we're going to defer the question of whether it's totally ordered. The next question is it reflexive? The answer is no, it is not reflexive, right? Because a value is not less than itself. So because it is not reflexive, it cannot be partially ordered. If it's not partially ordered, it cannot be totally ordered. So these are the only two properties that we can check for question number 4. All right, I'm not seeing any questions in the text channel. And now we move on to number 5. Consider the greater than or equal to relation over all integers. Which of the following relation properties apply? So this one is kind of cool because we look at reflexive and go like, yep, that is right, because a number, a value is always greater than or equal to itself. It is not symmetric. It is transitive. And it is also anti-symmetric. So this is one that is kind of interesting because it is antisymmetric, because if you have ARB and BRA, in other words, if A is greater than or equal to B and B is greater than or equal to A, then A and B must be the same. So it is antisymmetric. So with these 3 already checked, we can now automatically check partially ordered, and the only question left is it also comparable? If I just choose any 2 integers from the set of all integers, is one always going to be greater than or equal to the other one? I don't really care which direction. I just want to know, does it work one way or the other? And the answer is yes. So that means it is also totally ordered. So that's question number 5. And we got people typing, so I'm going to pause here. Alright, so because this relation is totally ordered, we can use it to sort a data set that uses valid elements for this relation. Yes, yep, exactly. So sorting does require something that is, well, technically it's not, because the negation of greater than or equal to is less than. But if you want to sort, you need something that at least from one perspective is totally ordered. That is true. So Nathan is correct. In order for greater than or equal to can be used as a comparison function to quicksort and some of the other sorting algorithms or functions where you can pass the comparison function as a pointer to the function itself. All right, next question. Rayshawn said, I thought you said the recorded lecture that if it is totally ordered, it's no longer partially ordered. Nope, I do not believe that's what I said. Everything that is totally ordered is also partially ordered, but not the other way around. Now, if I did say that, in other words, if somebody can actually go back to the recording and find the time when I actually said that, then I would admit to my guilt, because that would be wrong. I would have said the wrong thing in that case. But I do not believe that I said that. Okay. And Philip is still typing, so, and we got 3 people typing. So I'm just gonna scroll the screen and wait for those questions or comments. In the relation module toward the end, it states, you can see that the only difference between partially ordering and total ordering is the last item known as comparability. Furthermore, any totally ordered relation is also automatically partially ordered, or automatically partially ordering. Yeah, so, but I think what Rayshawn is saying is I said something differently in lecture, not in the notes. But I have no recollection that I said anything like that. But that's okay, because I have no recollection of what I just said, like the previous sentence or the earlier part of the sentence. So that happens all the time. It's called deniability. But since everything is YouTubed, so if I did say that, that would have it would have evidence. All right, so there does not seem to be any more questions. So we're going to move on to question number 6, unless I see some new text appearing in the text channel. All right, so question number 6. If R is a relation defined over X and known to be reflexive, which of the following do we know for sure, regardless of the actual definitions of R and X? So I like questions like these. I mean, they really make you think. All right, so are they the same? Do they have the same cardinality? They can, but not necessarily. R is greater than, the cardinality of R is greater than or equal to the cardinality of X. That looks promising. Are the cardinalities do not equal to each other? No, they can be equal. And the cardinality of R is less than the cardinality of X. That doesn't make sense, right? Because every element of X has to relate to itself. That means R has to have at least the same number of elements as X itself, which is this option over here. So that should make sense. And then Nathan typed in the text channel, to be reflexive, R needs to define a relation for at least every element in X. That is correct, and that is why we know the cardinality of R is at least as big as the cardinality of X. All right, last question. Question number 7. If R is a relation defined over X and R is known to be symmetric, which of the following do we know for sure, regardless of how R and X are defined? Well, I think that example that I showed you earlier should help answer this question. Okay, so we're gonna look at each one of these, just kind of individually and go like, can we make an R so that it is symmetric but not this? Let's look at the first one. Well, R can be empty, right? So there's no requirement that R has to have the same cardinality of X. All right, so this one doesn't work. And for the same reason, the cardinality of R greater than or equal to the cardinality of X is also not guaranteed, because R can be empty. Yep. It is odd. Well, if R is empty, then 0 is not odd, right? So we can cross that one out. And this one is also wrong, because if X has one element and R is empty, then this doesn't work. And so this one, does take a little bit of time to process, because if R is empty, then the cardinality of R being less than the cardinality of X can be true. Okay, but X itself can also be empty, right? There's no requirement that says X cannot be empty, so it may not be like this one either. R is even. Well, it seems to make sense, but it does not, right? Because if X only has one single element and R has that element relating to itself, then R has only one element as well, which is not even. The cardinality of R does not equal to the cardinality of X. Nope, there's no guarantee of that either. So the correct answer is none of the other choices. I like questions like this because I made it. All right, submit quiz. Let's see how I'm doing in this particular test. All right, so what am I getting? What am I getting? Come on, show me. So 1 out of 1, 1 out of 1, 1 out of 1. Woohoo! I got 7 out of 7. Yeah, I still got that little device. Cool. All right, so are we ready? Yep. The cardinality of R is greater than or equal to 0 is all we know. Yep. But since it is not one of the options to answer with that one, so the only one we can choose is none of the above. All right. So, any questions, comments about this particular homework assignment? I mean, the whole purpose of the assignment is really to make you think. Do I know what that means, right? That's kind of the way I design the assignments. It's not busy work. I really want these to be interesting questions, not too many of those, and I want these questions to really make you think. Do I really understand that word as the way it should be defined in the context, of this topic? And obviously, it doesn't always work like that. Sometimes I miss the mark miserably, but hopefully this time it kind of hits the mark a little bit. All right, cool. Yes, we are going to have homework in the current module. So we're going to continue with the topic first, right? We'll continue to talk about the topic. And we are not quite ready for assignment yet because I don't want you guys to do propositional logic the way that most human beings do it, because that would be a waste of time. And I'll explain why that is the case as well. So there won't be anything to do until we talk about what is conjunctive normal form and also resolution, because those two are super duper important concepts when we try to mechanize theorem proving. Theorem proving without mechanization is like, okay, you kind of know how to do that already. But I want to do it using a computer. I want to automate the whole process. So we won't get anything to actually chew on or to work on until that time. Well, I have my alarm clock set to take roll at a different time, so it's not yet. And not yet is a phrase that my cats actually understand, because they will try to get me to feed them at least an hour before the actual time. So I would tell my cats, not yet. And then they look at me as if they don't understand and kept, meowing at me. Yes, they want their payment in advance. All right. But I'm quite certain they understand the phrase, not yet. uh, all right. So let's go ahead and move on to all of this stuff here. All right, so I think we spent a good portion of the lecture on Monday to talk about how a transformation rule, basically an element of zeta, and remember we changed this from omega back to zeta because that was a typo. So make sure that your note is corrected if you printed it or saved a copy from before. So what we are going to do now is to move on to so what about all the transformation rules? What about this rule? What about that rule, and so on? So if you read ahead, in section 4, a useful example, I don't even bother to do it. I mean, I gave you some interesting ones, right? This one we looked at already. This one I believe we also looked at. And then we have this one we haven't looked at. This is basically De Morgan's law. The negation of phi or psi infers the conjunction of the negation of phi and the negation of psi. So that's basically De Morgan's law, and this is the other side of De Morgan's law. So if not phi and not psi exist in the set D, and if people are thinking, what D are we talking about? There's no set D anywhere. Well, I beg to differ, right? Set D, the notation of D is introduced over here. So the set D are a set of all the derivable well-formed formula. And the term derivable is defined also over here. Okay, that's basically that's pretty much all we did, okay, on Monday, was to define what is considered derivable. And it is it's a rule. Okay, if we fire a rule, meaning that all of these conditions are met, on the left hand side of the infer symbol, then we quote unquote fire the rule. And when we fire the rule, we basically just label another well-formed formula from W, the set W. And if people are thinking, which set W are we talking about? W is the set of all the well-formed formulae. And we basically label another well-formed formula, as derivable. So that was basically what we talked about on Monday, and this is also why it is super duper important to study ahead of time, before class, to reestablish the context that we left off in the previous class. Are the constraints axiomatic? What constraints are we talking about, Eric? I just want to be sure, what constraints we are actually referring to. In M. Nope, they are not. So M is basically just the left-hand side of a rule. It's basically a pattern for us to match, to see if we can find patterns. For each element of M, it is specifying a single pattern for a single well-formed formula that should be derivable. And if we meet all of the requirements in M, then we would have instantiated the Greek letters. So I forgot that I used rho instead of theta, in this module, but that's okay. So basically, we are instantiating theta, psi, phi, and psi, based on the constraints already met in M, and they all have to be met in order to fire the rule. So when we fire the rule, we would have known what each Greek letter should be instantiated to, and each one should be instantiated to a well-formed formula, but not necessarily derivable. But when we apply WFFQ, which is a well-formed formula, using theta, phi, and psi as the values, and then we basically use the instantiation at the time and say that well-formed formula is going to be derivable. So it was a long discussion, because there were a lot of steps, and there was a lot of abstraction, to talk about the mechanism of how a rule is applied from zeta. So but the short answer to the question is the constraints are not axiomatic. They're basically just patterns to be matched. All right, so moving on, we talked about these two, and then these two correspond to De Morgan's law, and there's a whole bunch more. Okay, so if you want to know what I mean by a whole bunch more, you can refer to not this one, but this one over here. So you can see that Wikipedia even used the same symbol, the infer symbol, which we know as V dash if you want to type it out in LaTeX. So we got P implies Q, P implies not Q, infers not Q, not P. Sorry, implies not P. because P cannot imply both Q and not Q at the same time. So P itself has to be false. That's the only way to make both implications true. What is the title of that page? There's a link from my module. That this is the link. There we go. All right, cool. So I'm just leveraging what is on Wikipedia already because I did not feel like retyping everything. Okay, there's no point in doing that. Also note that the notation, they use a single bar arrow as implication, and I use a double bar. The reason why I use a double bar is the single bar one is used to denote functions. So I cannot use the same symbol, in two different contexts, or I try not to. So that's why I use a double bar instead of a single bar. And Nathan put the link in the text channel as well. Thank you. All right, so there's a whole bunch. Okay, there's a whole bunch here. You can see double negation of P infers P. Okay, that seems to make sense. This one we talked about already. It's every single one has a name. Okay, and I'm really bad with names, so I'm not even going to I'm not even going to try to remember all the names. And then here's one where P and Q infers P and Q infers Q. Oh, okay, I see. So basically, if you have P and Q as a conjunction that is already in D, then P has to be in D as well. Well, that kind of makes sense, right? Because if P and Q is derivable, then P by itself should be derivable as well. All right. This page is a summary of almost the entire symbolic logic class. Yes. Yep. Exactly. And I'm not going to go through every single one of these, okay? Because it's a long list here, okay? And every single one has a name, right? So what is the whole point of bringing you guys here? Well, the only point to bring you here is to say this is hard, okay? There are a lot of rules that you have to remember, and remember we are trying to automate this, right? So we are trying to write a program and look at all of these inference rules and try to determine which one should I apply now in order to prove a very specific well-formed formula to be derivable. How do we go from iota, everything that is known to be true, and these are all given to be true, they are axiomatic, and I give you a specific expression and I'm asking you, is that expression derivable from iota over here? And you have all of these rules to consider, okay? And some of these are really kind of awkward too. Look at this one, okay? You have an empty set infers P or not P. I mean, it makes sense, right? Any well-formed formula or the negation of the same well-formed formula has to be derivable. It has to be true, okay? But is it going to be helpful? Well, maybe, maybe not. I mean, so you can end up going around in circles. And the most important part is, even if your iota starts off to be fairly simple, the W set is quite easily infinite. In other words, you're looking for a needle in a haystack, and the haystack is infinitely large. Now, I'm saying it's a needle. Even though the well-formed formula is well-formed, in other words, we know it is in W. But the question is it in D? We know that D is a subset of W, right? And we also know that D is most likely infinitely large as well. So now the question is, if I just give you a well-formed formula, it is known to be in W, and the question is it in D? It's a tough question to answer because if the space that you're searching in is infinitely large, then it is very difficult to differentiate between maybe it's in the haystack but I haven't gotten to it yet versus maybe it's not actually in the haystack. Those two cases become very difficult to differentiate. So you might end up, just letting a program run and run and run and run, and then 60 years later, the program is still running, and you still cannot know whether maybe that's not a theorem versus maybe I have not found a path to that specific theorem yet. So those two cases cannot be differentiated, which is a problem. All right, so we got some traffic in the text channel. So how do we use it in a way that we can actually apply to proving theorems that's actually effective? So that's why we need to move on to talk about resolution and also conjunctive normal form. So thank you, Nathan, for kind of bridging to the next main topic, but it's also still in this module. And then Philip asks, so what is the difference between implies and infers? Now, that is a very, very good question. Infers is just saying whether it's derivable. It's a very syntactic, mechanical type of if these patterns match, and then we just use these specific matched pattern, plug those into that well-formed formula, and then that other formula, the one that's on the right-hand side, becomes quote-unquote derivable or inferred. So that's a mechanical thing to do. Implies, on the other hand, is dependent on the meaning of stuff. So implies is used when you are proving a theorem, and infer is what you use when you have a mechanical system, hopefully that it mirrors all of the same things that you do it by hand, but it is mechanical. So I'm not really sure whether that answers the question or not, Philip. One is syntactic, one is semantic, and that's the main difference between the word infers and implies. Infers is syntactic, implies is semantic. All right, cool. I can give you another example. Okay, I can give you another example. Let's think about the design of a car. Okay, from the safety perspective. Okay, so in the past, okay, Toyota, all car manufacturers would have to actually make a scaled down version of a new chassis and test crash it like there's no tomorrow, until they say, okay, I think this chassis is strong enough or it's secure enough, the occupants will not be severely injured in certain types of accidents. But we know that is not being done these days because there's finite element simulation, right? So we have computer tools that can simulate physics to the point where it is accurate enough to predict whether a specific chassis design is going to be safe or not. So this is kind of like that, okay? So in the good old days, we all have to apply these logic by hand, and we go like, okay, here's De Morgan's law, and here's the distributive law, and so on and so forth, and then we derive equations, right? Not equations, but we derive expressions. That's how things were done, okay? Just like crash testing at cars, the chassis of a car, repetitively to find out whether it's safe or not. So over time, okay, computational resources improved, and we don't have to crash test cars physically anymore. Because of what? Because simulation is resembling with sufficient accuracy of the physics involved when you want to study how a car is going to crumble in a car collision. Okay, so what we're trying to do is exactly the same thing here. Okay, we're trying to derive a system, an automated system, where the syntactic rules is going to resemble the way that we actually apply reasoning. I shouldn't say close enough, that's the first phrase that I was thinking about, but I would say exactly the same way that resembles or match how we do the proofs. Okay, so when the syntactic system, which is kind of the simulation thing, matches reality, which is how we do how we derive the conclusions out of logical facts and axiomatic facts, then when those two systems match, then everything is good, right? Because now we can say if the system concludes this is not a theorem, we know it is not a theorem. Okay, because if I had done it by hand, I would have come to the same conclusion. If the system says this is a theorem, then I know that I would have come to the same conclusion if I were to do all of these steps by hand. So that's the kind of the difference, or the relationship between the word infer, which is simulation, versus the word implies, which is not simulation, using the actual meaning of Boolean algebra to carry out the derivations. All right, and then Luke said, not P infers P versus P implies Q. P implies Q and Q implies R infers P implies R versus P implies R. All right, so all right, so implication in what Luke's sentence is a it's an operator, okay? Because there are two implications. There's one implication when we use an implication in a proof, but in the context of applying a transformation rule, that implication is no more than just a symbol. Okay, it is just a way for us to differentiate between all of the quote unquote Boolean operators. So so that implication is nothing more than a symbol. It does not actually have the meaning of imply as we know it. All right. All right. So let me see. Let me check the time. I'm gonna give you guys the word for the road taking thing because I know some people have been waiting for it for a while. Well, this is the funny story from yesterday, from CISP440, because 310 has actually a lot more students compared to this class. As soon as the word for road taking was disclosed, I would say within 5 seconds, people were just getting off of the screen share channel, the voice channel. It was that obvious. It's like within 5 seconds, people were just dropping off, and that was like about 30 minutes into the lecture. Yeah, I think some people are just looking at it as, oh, I just need to clock in. I'm not going to comment on the Alright, so the word that I have chosen is DARPA, all in uppercase. And I'm going to release the quiz. I'm going to double check the time first. I don't think I have a time set yet. Alright, so I'm going to set it to all the way until the end of the lecture. That should give people plenty of time to do it. There we go. Save and publish. There we go. Alright, so you guys can go ahead and take roll, and I am getting back to my module. And what I'll do is I'm skipping section 4.1. It is important, okay, but the current direction of our discussion points to section 5. So I will get back to section 4.1 later on. But section 5 is significant for a very important reason. Alright, so I think we are all ready to move on to resolution logic here. Alright, so this is a proof, okay? This is using Boolean algebra, okay? So using Boolean algebra, I can do this derivation. So the first thing that I did was to use the definition of implication. So I negate the left hand side of the implication or the right hand side of the implication, and that's why you see this negation symbol over here. From the first line to the second line, I see faces. Oh, okay. I see. I got a bunch of things that pop up in my mind, like bubbles in a soft drink, but I'm not gonna say anything because some of that may be considered very politically incorrect. So I just leave it at that. From the first line to the second line is the application of De Morgan's law, because we have a negation of an and over here. So we ended up negating the individual components and connecting the components using or, because that's how De Morgan's law work. And then on the other side, we are dissolving the parentheses because of associative law in Boolean algebra. And then from the second line to the third line, we apply De Morgan's law again, because this time we have negation of a or, negation of a or. So we convert that into the negation of the components, and then we change the or to an and to connect the negated individual components. Do the same thing over here, and yes, I admit that I simplified one. I applied two steps in at once, because it's supposed to be the negation of psi, and I just simplified negation of negation to just psi by itself. So I skipped one step over here. From here to here, I introduce n1, because anything is the same as anything or excuse me, and true. So and true doesn't really change anything, but it doesn't hurt anything either. So I'm just introducing the and true over here, and then that true eventually becomes psi or not psi. So this is one of the applications of that kind of strange rule that we saw earlier. From an empty set, we basically go like, oh, just choose any well-formed formula, and if you OR that well-formed formula with the negation of itself, then we have something that is known to be true. So that's this is one application of that. From here to here, it is distribution. So distribution works kind of the same way as in normal algebra. And then from here to here, oh, I thought I heard something. And then from here to here, we have, let's see, I believe it is moving things around a little bit and factoring. And then from here to here, let me see. We have a simplification, because I group not phi or phi, and that is just true. And I also group rho or not rho, that is also true. So that's a simplification. And then from here to here, we have simplification again, because one and whatever is just that whatever. Anything and one is just that anything. And then from here to here, it is also simplification, because we have not psi or psi, which is just one, and then one or whatever is just one. So this is a proof to say that doesn't matter what the values of phi, psi, and rho are, this statement, this implication, is always going to be true. All right, so yes, so Chris makes a very good point. So for those of you who want to kind of practice your Boolean algebra, you can go ahead and quote, like, what was the actual step being taken, what algebraic rule was used to go from one step to the next. It's a good exercise. Anyway, so getting back to the significance of this point here, because it doesn't look significant at all. So this true here is basically saying this implication is always true. Now, you can say, but in order for an implication to be always true, all we have to do is to make the left-hand side false, right? Well, but we are not relying on that trick here, okay? This part here, this conjunction, doesn't have to be always false. So this implication is always true, meaning that if you can find me an expression that says phi or psi, if you can find me another expression that says not psi or rho, and these two expressions are connected by a conjunction, which means they're both true at the same time, then I can tell you that phi or rho is also guaranteed to be true. That's right. Yep. Implication is not A. A implies B is the same as not A or B. That is correct. And that's the definition of implication. So I negate this entire side of the implication, which is why we see this negation symbol over here, and then it's ORed with the right hand side of the original implication. So Chris and Elijah are both correct in terms of explaining what happened on the first line. All right, so what is the significance of this? Okay, the significance is the result of the implication lost a term. Because originally we got three terms, we got three individual Greek letters. We got phi, we got psi, and we also got rho. And then the implied result or the consequent only has phi and rho. Psi is gone. Okay? And this implication is always true, which means, oh, we can put this into our transformation rule, right? Because any implication that is semantically derived can turn into a transformation rule just by changing the implication into an infer symbol, right? So now we can say, oh, okay, we can now add this kind of really awkward and odd inference rule into zeta. So that by itself doesn't seem to be particularly interesting or worthwhile to understand. It's like, okay, so what is the big deal? So the other big deal is you can give me any Boolean expression as long as it is valid. In other words, if you give me any well-formed formula, okay, based on what we know about the operators and whatnot, I can always turn it into what we call a CNF. Okay, so that means, so now we move on to the concept of a CNF. So this is how we talk about the definition of CNF over here. So okay, so I don't have enough time to actually go through the actual detailed definition of a CNF. So CNF basically means you have the last operation is a conjunction, but the values that are being ANDed together, each one is a disjunction. And then inside each disjunction, you can only have variables or the negation of variables. That is a CNF. So let me just illustrate to you, what a CNF looks like in a specific case. So we're going to pick alpha to be kind of the same thing as usual. So we have P, Q, R, S, T, and this time I'm going to go back to well, I'll just be consistent with my previous note. So we got theta, we got psi, phi, and then we got psi. So that's a pretty usual way that we define alpha. And based on this, okay, let's look at what is a CNF. Okay, so a CNF, okay, I'll give you several examples. So a CNF is basically a conjunction of disjunctions, and then inside each disjunction, it can only have variables or negations of variables. So that means this one, okay, we have P or Q and not P or T. That is CNF, okay, because right here we have a disjunction of two variables. Right here we have a disjunction of the negated variable and another variable, and then these disjunctions are ANDed together. So that makes this a CNF. Let's look at another one. Okay, so P by itself is also a CNF. So conjunctions of disjunctions is the only nesting allowed. Yes, that is the only nesting allowed. Negation can only be applied to variables. So that's the other rule that is kind of important. So P by itself is actually a CNF. And people look at this and go like, but where's the disjunction and where's the conjunction? Well, I can always coerce it to look that way, because we can say, here's your disjunction. And you go like, okay, but where's the conjunction? I want to see that conjunction. Well, if you really want to see that conjunction, we can always say conjunction with 1 or 1. So now I have just coerced it to look like a CNF, right? Because it's I know it is kind of pointless, right? Because anything or false is just that anything. It doesn't really change the value. We have true or true over here. Yeah, it's just true by itself, but it does look like a disjunction, doesn't it? And then now we have a conjunction of the two disjunctions. I mean, it doesn't really change. It really is just P, okay, by itself. But I can make it look like a proper CNF. That's the whole point. Okay, I can use constants, in order to make it look like a regular, quote unquote, regular, CNF. So are we doing okay so far in terms of what is considered a CNF? You have the last operation has to be a conjunction. Now it doesn't have to be just one single conjunction. Okay, let me use the other one as a starting point. So it doesn't have to be a single one. In other words, you can string along a bunch of conjunctions, and then inside this one I can say it's Q or S. In this case, I mean, this is just an example, but basically you just have a bunch of ors, and the result of the ors are ANDed together, and inside the ors you can only have variables or the negation of variables. That's it. Okay, so those are the basic rules. And let's see, what time is it? I still got 2 more minutes. Okay, and I think that's enough time to make this last point here. The last point is, why is CNF interesting? What is the big deal of CNF? The big deal is I can turn any Boolean expression into CNF. You can give me something that looks really ugly with implies, if and only if, negation of conjunction inside the disjunction, and so on and so forth. Okay, you can nest things in a very nasty way, and I can turn it into a CNF. So that's kind of big, right? This is kind of huge, because what it's telling you is any Boolean expression can be expressed as a conjunctive normal form expression. That is kind of big, right? And now I have to make the last point. We got 1 minute left. Okay, so the last point is, once you have CNF, don't you think this kind of resembles something that we were looking at earlier? This is what we need to apply resolution. So resolution, CNF are closely related, because one is CNF is basically saying, okay, give me any Boolean expression, give me any well-formed formula from W, right? And I can turn it into this really awkward looking form. Okay, it is still well formed, but it looks kind of awkward, right? Because we just have a conjunction of a whole bunch of disjunctions, and inside each disjunction we can only have variables and negated variables. But once I have my CNF, I can then apply resolution. So resolution is interesting, okay? Because every time we apply resolution, this is resolution expressed as a transformation rule. But every single time we apply resolution, guess what? We lose something. The result is always simpler than what we start off with. Now, this is huge, because many of the other transformation rules only make things longer and more complicated. This one is exactly the opposite. It always makes things less complicated than before. So without actually going through the actual proof, I think most people are now saying, oh, so with this and CNF, are you implying that the space of all the well-formed formulas are now finite? That is exactly what I'm trying to get to. So now we have a finite space, which means there's only a fixed number of elements. It can still be huge, okay? But we know it's finite. Okay, now once you have a finite space and you need to see whether something is derivable in that finite space, that is a good problem to solve, because now you can say, well, it might take a while, but I can conclusively tell you whether a specific expression is derivable or not. And the amount of time is also predictable. I mean, it's going to be bad, but it's not going to be infinite. So that is that's the connection, okay, of what we just talked about at the beginning of the lecture. Automatically proving something using a mechanical system to do something, and now we have a way to do things very, very mechanically, and also at the same time we know it's going to conclude one way or the other. We are going to conclude because the space that we are searching in is finite now. So those are the kind of like the overall view of things that are that are important. So I think it's really important to look at both the details, pine needles, so to speak, the branches, one step up, from the pine needles, the pine trees, okay, one level up. But looking at this, and say, oh, we are relating this all the way back to mechanical theorem proving. That's looking at a forest, okay? But that is also important because that's how we can understand how these topics all connect to something that potentially can be your career in cybersecurity. All right, so I am done with my content. I'm just going to catch up with the text channel. All right, so conjunction of disjunction is the only nesting allowed. Yes. Okay. ORS with variable negation of variables joined by AND. Yes, ORs. Okay, yes, disjunctions with variables or negations of variables joined by AND. Yes, that is correct as well. Elijah said, so CNF is just breaking it down to the conjunction of disjunctions. Yes. And Chris said, is resolution a general idea of or that specific rule? It is just that specific rule. So resolution refers to this implication here, and also, depending on the context, it can also be referring to the transformation rule, which is basically the implication, but expressed as a transformation rule. And then the next one is, so we will be able to transform any combination of Boolean well-formed formula to CNF form, and we use CNF form to resolve the expression to a single value. Yeah, that's kind of the idea. Sometimes it's doable and sometimes it's not. Okay, so there's one more element to this whole thing. Okay, because we now have the basic ingredient, but we're missing one super duper important thing, which is proof by contradiction, or the concept of proving proof by contradiction. So we'll talk about that next time. Can I talk about the makeup test for Monday? There is a makeup test on Monday. I mean, other than that, I really cannot tell you much about it because I have not really made up the questions for that test. Next, CNF homework due Monday or not? Nope, it is not due Monday because I have not shown you how to convert any general expression to a CNF, so no homework due at this point. Not with exam, please. CNF homework. Please go easy on makeup exam. Well, those words are usually wasted on me because I mean, I really don't try to make the test super duper hard, but I have to make it somewhat challenging so that I can tell whether you guys are understanding the concepts or not. Yes, it doesn't hurt to try, right? As they say. And I still got a few people typing, so I'm gonna keep the channel on. Is the exam on class time? Yes. If everyone gets 100%, you are not really testing how much they know. Well, not exactly, because it is entirely possible the entire class know the topics that we have been talking about, through and through. So I would not say it's impossible. In other words, I'm not going to do the thing where, some professors, would look at the test results. If everybody get a good score, they will artificially introduce, B's and C's, in the class because, they do not believe, the entire class can really do well, in a test. I don't really hold that belief. Okay, I do believe that it is possible the entire class can do really well. So I will not artificially give people a lower grade. So my grades, the boundaries of when an A or B or C, happens is absolute. Okay, in a certain sense, because if you have 37.5%, you have a C. Okay, if you have 62.5% or more, you have a B. If you have 87.5% or more, you have an A. So that is absolute. Okay, it is compared against my standard and it's not relative to the rest of the class. All right. So I like the idea of a larger spread in the grading scale. It's called differentiating power of a test, and without trying, my tests usually end up that way. So when we get that contradiction component, proof by contradiction component, we will be able to finish solving Boolean well-formed formula. Yes, not solving per se, but to prove whether a well-formed formula is a theorem or not. In other words, can it be derived from the elements of iota? So yes, so uh, after that clarification, what Nathan said is correct. So those are all the very important pieces. Each one by itself is interesting and in a certain way abstract to begin with, but when they are combined, then we finally have this tool that we can use for automated theorem proving, but only limited to propositional logic or propositional calculus, because propositional calculus itself does not include quantification. So when we introduce quantification and parameterization, then we're talking about predicate calculus, which is a more advanced form of how to specify logic. But we'll get to that one too. Hopefully we'll have time to get to that one. All right. So I'm just checking on the channel. So it's limited by the constraints of the system. So it's easier to cover all cases. Are you referring to predicate calculus or propositional calculus? Predicate calculus is more expressive because you can now specify rules that involve the use of variables, and it can also use quantification. Propositional logic does not do that. It can only capture simpler type of logic. All right. I'm really unsure how to study for the test without having any idea of the format. All right, so this is getting back to the format really should not have anything to do with the understanding of the material. The concept of intersection, the concept of union, the concept of subset, this concept of element of, okay, the concept of functions, injection, surjection, bijection, the definition of G, the function that we introduced in Aleph Null. So that is the starting point, right? Because that's knowledge and that's also definitions and so on and so forth. The exam is about the application of such knowledge in order to figure out certain types of problems. So I'm just gonna say the format really should not have a whole lot to do with how people study, because the exam is not about repeating a known process step by step applied to different variables in the test. So it is about using the knowledge that we have already introduced in this class, including all the definitions, in order to solve specific cases. Anyone know the class scale? I missed what professor said. I'm not really sure what that means. Anyone know the class scale? The grading scale? Oh, percentage? So 37.5% is C. Oh, okay, let me start with a D. So 12.5% is a D. 37.5% is a C. 62.5% is a B. 87.5% is an A. So these are the threshold to get into a specific grade. I mean, anything less than 12.5% is an F. I don't think anyone's going to argue with that. I hope not. Certainly hope not. But tech, I got 11%. I think I deserve at least a D. It's 87.5%. Yep. Okay. You got me. There we go. So it's 87.5%. I mean, these are just 1/8, 3/8, 5/8, and 7/8 because your GPAs are at the quarter marks, right? 0%, 25%, 50%, 75%, and 100%. So all I did was to expand from the midpoint of each letter grade 12.5% this way and 12.5% the other way, so that I have a range of percentage for a specific letter grade corresponding to 0, 1, 2, 3, 4. So I'm just using the GPA scale for grading purposes. So what you're saying is all those years of rote memorization they taught us in public school won't cut it anymore. Well, it depends on what it is, right? If you are on an assembly line, putting together a Furby and you're trying to do as quickly as possible, I would say rote learning still applies. I mean, practice makes perfect in that case. Yeah, I cannot make any promises based on to be consistent with what Luke said. I would say Luke's statement is based on certain observations in the past, but that pattern may not be applied in the future, so there's no guarantee. Yeah, so calculus is, yeah, exactly. So you have to understand what it means, even though you may not be doing it by hand. So it's about the application. So once again, it is about the application, because your job is going to be about application. It is not going to be about, there are no really known steps to follow when you are a software engineer or when you are a programmer. I mean, the whole process of debugging is not, it's not procedural. It's not like, we just follow these steps, 1, 2, 3, 4, A, B, C, D, and you get it done. Sometimes it may take you 5 minutes to locate a bug and fix it, easy peasy. And other times it might take you weeks to find one. So, yeah, it's still being recorded, because I don't really feel a need not to record it. Because we still got a few people conversing right now. You might not be writing data structures, but you should understand how they work when you use them. And more importantly, people should also understand what is time complexity. What is the quote-unquote big O notation? What does it mean when you have a big O notation? By the way, it's actually not O, it is Omicron. It's big Omicron. I'm curious, why did you choose to have the grading scale this way? Because I grade everything based on A, B, C, D, F. And that scale is already spelled out in the syllabus. What I consider as A, B, C, D, F. So I just look at various aspects of an answer and evaluate that based on that scale and go like, okay, I think this part of this answer is an A. I think this part of this answer is a B, and so on. I feel that so long we can understand the prompt more easily. Yes, so if the prompt itself is not easily understood, let me know. Okay, even during the exam, I can clarify and provide, possibly provide examples to illustrate, how to interpret the questions. So keep that in mind. Okay, if you're not sure what the question itself is asking or how to interpret the question, you can ask me about that. And I will try my best to respond to those questions without giving out the answer or without giving out any knowledge that is actually being tested in the exam. Yep, Chris is right. 0 to 4, F to A, 100% divided by 4. Or if you prefer, you can also use the star system of Amazon, right? You have 1, 2, 3, 4, 5 stars. So there are 5 individual quote-unquote grades that you can give to products and services and whatnot. Same thing over here. All right. Well, it is unfortunate, and that's because I make assumptions about what people understand, and sometimes my assumption may not be 100% applicable. That's why. Like in the previous test, I actually read my question several times and go like, is that clear what it's asking? Yeah, I think so. Let me read it again. Is it clear what I'm asking? Yep, pretty clear to me. Yes, the scope is going to be the same. The scope has not changed. So the scope is the same as the version 1 of exam 1. It's still going to be covering the same material. It is excluding relations. It's including functions. It's including aleph null. So aleph null is the last topic in terms of written modules in Canvas as far as the scope is concerned. Yes, till aleph null and including aleph null. All right. Yes. So it's an affirmative, Mohammed. The 5-star system. I mean, the way I look at so the way I look at ABCDF is explained in the syllabus. And I really try my best to make it clear what each grade means when I wrote the syllabus. But some of these things may not be as easily explained as others. So a 0 is no work is submitted, or the submitted work shows no evidence of the ability to analyze and think critically, or the ability to synthesize or problem solve, unless otherwise specified. Code that does not compile or assemble, which does not really apply to this class for the most part, those would all be zeros. 1 means the submitted work shows some but insufficient evidence of the ability to analyze and think critically, the ability to synthesize or problem solve, or the familiarity and efficiency do not matter in this case when people get a grade of 1, and so on. All right, but not the Uber Lyft 5-star system, where anything but 5 stars means you want the driver to be fired. I have not used Uber or Lyft, so I cannot attest to that ranking system. Yeah, you guys can drop off. We're just chit-chatting right now. Well, if we encrypt our answers, would that be a 0? Well, if you give me the key to decipher and I can actually see your answer, then it's going to be okay. If it remains encrypted, then it would be considered as no work is submitted, or it shows no evidence, because all I see is just a mumbo jumbo bunch of bytes. Wow, that's like Berkeley standard. If you want to go to Berkeley, from high school, you need a 4.7 GPA to even be considered. If you have a 4.65 GPA, they just put it into the firewood pile. Oh, that is rough, man. Alrighty. Alright, so I think it's safe to stop screen sharing and YouTube at this point. So I'm gonna sign off from the voice channel, but I'll probably still be on the text channel on and off. So if you guys need to talk to me about anything, just